Let's talk about dopamine in the context of learning, because that's something that I think most people don't associate with dopamine. What are a few examples of what we know about dopamine and its role in learning?
That's a world I can't even summarize in a quick way. People that work on rodents now will take a genetically modified rodent and they will study the way in which dopamine release correlates with something the animal is learning. The animal may learn to turn left when it sees a light. It may learn to run toward food. It may learn to run down a maze. All kinds of learning tasks associated with the animal are associated with dopamine fluctuations in your brain. Now, these aren't global. They're all over the place, but there are different kinds of signals that you can find in different spots in your brain. And we've begun to understand dopamine as a central player in the algorithms that your brain runs. And that's where people like me, and people like me, computational neuroscientists, have made a connection. And that's the connection between the kinds of learning rules and learning procedures that are installed in your brain and installed in the brain of every mobile creature on the planet and dopamine fluctuations. So that's a strong connection that has been worked out over the last 30 years. The algorithms are well understood. What wasn't well understood 30 years ago was the kind of remarkable things those same algorithms can learn. I'll come back to that. I mean, there have been a bunch of modern breakthroughs in what's called reinforcement learning. And reinforcement learning's main biology partner is dopamine. It's the first big hit. Now, it's an area of science. And so what happens when you have a big finding that looks like it explains a lot of things? Well, people come rushing in to sort of beat it up. That's their job. That's their job, to hack away. Oh, is it really this? Does it work the same in this context and that context? But I think the description of what dopamine does as a learning rule is pretty much true. Let me give you an example. So psychologists since the time of Pavlov have understood what it means for an animal to generate a prediction and to compare it to an outcome. Okay, the example is, so today's Wednesday. Suppose, and this is Rich Sutton's example, suppose I make a prediction today that it's going to rain 2 inches on Saturday. Okay, now we're going to fast forward to tomorrow, and I'm going to update my prediction because I have new knowledge, and it's going to say it's going to rain 10 inches on Saturday. Okay, there's been no reinforcing feedback. It hasn't rained yet because it's not Saturday yet. I'm making a prediction about Saturday. But there's a difference between this expectation and that expectation. Those differences are encoded by dopamine. It's called a temporal difference error. And dopamine seems to code that before you ever get to the terminal return. Imagine that you were playing a game like checkers. You make a move in the game, and you might make 40 moves before you win the game. And suppose winning the game is the reward. Well, you may have some prediction. Your brain makes a prediction when you play board position to board position that you're going to win the game, and that's a fluctuating quantity. That's a different kind of learning rule. The kind of learning rule that psychologists talk about, that you think about in your everyday life, is it's going to rain 2 inches today. Okay, how much did it rain? Okay, so that's a comparison between an outcome and your expectation. What Rich Sutton and Andy Bartow did was said, well, what you really want to do is you want to stick between there your next prediction. So you want successive predictions, okay? And why is that a good model for animals? Well, because if you're an animal and you're wandering around foraging, mainly you're not finding anything. You're going from position to position to position to position to position, but you're learning. And dopamine is encoding those signals.
I'm so glad you said the word foraging, because I want to hover on the theme of foraging in the context of human decision-making and learning and behavior. So to stay with your description, Saturday rolls around. Let's say it doesn't rain. Let's say the person doesn't want it to rain. They're not a farmer. They want to go to the beach on Saturday. Mm-hmm. Now we can talk about reward prediction error. Right, the difference between the expectation when it actually happens.
Okay, let me interrupt and correct that a bit. The reward prediction error that people talk about dopamine representing is the prediction error that you get for every single step, whether or not you've received reward. That's kind of diffused out in the psychology literature as you have an expectation and you have a reward. Mm-hmm. It may be positive, negative, or zero. Mm-hmm. And what you do is you make an error there. That was understood in the 60s and 70s. It's called the Rescorla-Wagner rule, 1972. That's how the system should learn. The fact is, though, that doesn't model reality very well. Reality doesn't give you feedback like that every time. Reality often gives you long stretches of nothing. The insight, I think, of Sutton and Bartow in their algorithm was, well, a better algorithm for learning continuously is to take successive predictions and to say that's a learning rule. Obviously, it's a learning rule with the outcome, when you get an outcome, when it's not zero, but it's successive predictions. It's like why that should be such a deep idea is not clear to me. What is clear to me from data is an algorithm based on that is installed in bee brains, sea slug brains, all the way up to human brains. There are these temporal difference reward prediction errors. And so I guess I'm sitting here trying to backwash the old version of it, which is people say in a kind of vernacular way, oh, it's the difference between your expectations and your reward. Yes, when that happens, but most of the time that's not happening, in which case it's the ongoing difference between your expectation and your next expectation. So it's fluctuations in your expectation as you move through the world. The DeepMind guys in London who beat the world Go playing champion and made AlphaFold and won Nobel Prizes, and I mean, they're starting in 2015, they just had this unbelievable series of hits. They use the Sutton and Bartow algorithm. They trained those systems where people would make, the computer players would make hundreds of board position changes before you ever got to the end of the game and update and learn based on that. They threw other tricks into. I'm not going to get technical about it. So there's a difference. It's not just expectation and outcome. It's expectation, next expectation, current outcome. Mm-hmm. And that is what rolls through. And that is what we see installed in, we have a paper this week coming out on honeybee brains where you can show the same sorts of learning rules in honeybee brains. In honeybee brains, it's probably octopamine, not dopamine. But the other thing to say about dopamine is it's not just dopamine. It's very clear that lots of neuromodulators like that are fluctuating with learning and motivation, and probably the whole symphony of them that creates motivation states and things like that.